You have to achieve one of these representation, right? So in order to achieve one of these representation, what are the things that are common in between? Okay, for example, if you think about number 1 and number 3, what are the things that is common in between? You will find that a and bk coefficient, ak and bm coefficients are the common, right? So as long as you know the coefficients ak and bm, so ak coefficients are the coefficients for your past outputs and bm coefficients are the coefficients for your past inputs, right? That is yn minus k, and this is for xn minus m. So between 1 and 3, these are the common thing. And if you think about FIR filter specifically, then you know that for FIR filter, your h of n is same as bm coefficients. Do you agree? Do you remember that we talked about FIR filter and we found that FIR filter coefficients are same as the impulse response sample values? Okay, so this is for FIR filter. So essentially, when we're talking about filter design, we're actually talking about getting the coefficients right. If we know the coefficient, then we'll be able to achieve these frequency response or system function or difference equation or the impulse response, right? And once you know any of this representation, that means you know about the filter. That means the filter design is done. Okay. Now we'll talk about what are the basic technical specification that is available for FIR or IIR filter design. Okay. And then another part, for as far as the filter design is concerned, another thing is that you should always start with a low pass filter design. Okay, does not matter whether your target filter is a low pass, high pass, band pass, or band reject. You always start with a low pass filter. So there is another part. So you always start with a low pass filter design. The first step will be low pass filter design. Okay, because from low pass you will be able to design high pass filter. Do you remember how to convert a low pass filter into a high pass filter? For example, the low pass filter is h of omega. Then the high pass filter will be h of
Omega minus pi.
So you can always convert a low pass filter into a high pass filter. Similarly, if you combine low pass and high pass, if you combine these two, you'll be able to find out band pass or band reject filter, right? Or band stop filter. Okay. So the idea is that always start with low pass filter. So low pass filter design meaning that achieving the frequency response of that low pass filter. That means HLP of omega or HLP low pass of Z, the system function. Okay. So this is another thing. So there are some example here. So let's say that this is an ideal low pass filter frequency response. So this is an ideal scenario, ideal response, okay, with a cutoff frequency of omega c. And then to see that you can have a two different low pass filter to make it a high pass filter. So one way is that convert the low pass into high pass by shifting your frequency response of low pass filter by amount of pi. Another way is that by combining two low pass filter, you will be able to achieve a high pass filter. So how it is? So you see that this is a low pass filter, but this time the low pass filter has a cutoff frequency of a pi. Okay. This is another low pass filter which has a cutoff frequency of omega c. Now remember that pi is basically the highest frequency possible. Okay, highest angular frequency possible, because your h omega or x omega is actually between minus pi to plus pi. So that is the highest angular frequency possible. Okay, so when you're talking about a low pass filter with a cutoff frequency pi, we're essentially saying that it is a low pass filter with a cutoff frequency pi. At the same time, this is an all pass filter. Okay, because if you think about from 0 to all the way pi, and pi is the highest angular frequency, that means you are covering each and every frequency, right? So that means it is actually all pass filter. It allows to pass all frequencies. But this all pass filter can also be considered as a low pass filter with a cutoff frequency pi. This is also true. Okay, so if you have two low pass filter, one is having cutoff frequency pi, another with cutoff frequency omega c, and you subtract the second one from the first one, you see the subtraction is there. Okay, so and then you will be able to get the high pass filter. So if you subtract, what you will going to have, basically you will get this, right? This kind of, if you subtract the second one from the first one, the bottom one from the top one, then you will get this kind of response. So what is this response? This is same as high pass filter from omega c with a cutoff frequency omega c. So this is exactly what you found. This is a high pass filter now with a cutoff frequency of omega c. Okay. So similarly, we are saying that if you have a two low pass filter, one with cutoff frequency omega c2, another with omega c1, and then you subtract the second one from the first one, you will be able to find out a band pass filter, right? So this is the pass band, and these are the stop band. With a lower cutoff frequency of omega c1 and higher cutoff frequency of omega c2. So the idea is that to build a band pass filter, you have to have two low pass filter, one with omega c2 and another with omega c1, and this one minus this one will be your band pass filter. So remember that the second low pass filter having an omega c1 will be lower than the first low pass filter's cutoff frequency omega c2. Okay, so that's the condition. Now if this is the other way around, now let's talk about band stop filter, how to design a band stop filter. You take a band pass filter, so basically you take one low pass and one high pass, okay, and that will be a band pass filter. So it's like this. You have one low pass filter here with omega c1 and another high pass filter here with omega c2. Okay, so you know how to design a low pass filter. You also know how to design a band pass filter with, how to design a high pass filter with the cutoff frequency omega c2, right? The last slide we talked about that one. So you now you add these two, it will be a now band stop filter. So between omega c1 to omega c2 will be your stop band, right? So the idea is that you can always start with low pass filter. So that's the point that we're trying to make. Now, regarding the specification, usually we talk about the magnitude specifications, right? As we mentioned that frequency response means it can be of two types, right? One is magnitude response, another is phase response. But for this course, we only stick to magnitude response and not the phase response, okay? So if you think about the frequency response, by default that now we are actually referring to magnitude response. So it can be of two types, okay? One is the absolute specification, another is the relative specification. So absolute specification is very simple. So for example, if you say that your cutoff frequency is let's say 50 hertz, okay? Your cutoff frequency is 50 hertz. This is the absolute specification. Now if I say that our cutoff frequency will be with respect to the sampling frequency or the maximum frequency of the bandwidth, okay? So in that case, it will be a relative frequency. For example, if I have a signal with an fs, say 500 hertz, okay? What would be my f maximum? According to Nyquist theorem, if I have a sampling rate of 500 hertz, what will be the highest frequency possible?
1000.
No, it is actually half.
250.
Right? So it will be 250 hertz. So if I now say that our absolute specification of the cutoff frequency is 50 hertz, but if I say that the cutoff frequency, the relative specification, R for relative, will be with respect to, it is actually relative to the maximum frequency. That means 50 by 250. Okay. So when you do normalization or take the relative value with respect to any maximum value, that means your maximum relative value will be 1 because your maximum frequency is 250. It cannot be more than that, and you are actually normalizing the value with respect to your maximum frequency. Okay. So it will be always 0 to 1. The value of your relative frequency will always be 0 to 1. Similarly for omega, okay, for omega max, what will be the value of angular frequency as mentioned before? It is minus pi to plus pi, and we do not take the negative frequencies, right? Because they do not make sense. So it is actually from 0 to pi. So what is the maximum omega? It is actually pi. So let's say that your cutoff frequency is actual cutoff frequency is, let's say, 0.5 pi, but when you take the relative frequency, it will be 0.5 pi divided by pi, because with respect to the maximum of omega, and it is eventually be 0.5. Okay, so that means when you take the relative frequency or relative specification, it becomes, between 0 to 1, because you are actually normalizing the value with respect to the maximum value. Okay, so sometimes, so this is the concept of relative. Now in this case, what is the relative specification? It is not only normalization, but also taking the value in log domain. Okay, so the relative specification not only taking the value in terms normalizing the value, but also taking the value in log domain. Okay, taking the in decibel scale. So that is the formula, minus 20 log 10 of h omega, the magnitude of h omega divided by h omega max. So let's see an example and we'll understand what is the difference between absolute and relative frequency. Okay, so now let's talk about the absolute specification. So what is the practical characteristics of an FIR or a typical filter? Okay, so this is the typical characteristics. So this is what we have plotted here, is actually h of omega, the magnitude of h of omega. Okay, so this is what we have plotted. So you'll see that so we have plotted with respect to omega, right? So this is a, practical characteristics of a low pass filter. So this is a low pass filter example. So this low pass filter, as it is not an ideal one, is a practical one. So you see that from pass band to stop band, the transition is not immediate, is not instantly, right? It takes some time. So, and then in the pass band and in the stop band, it is not, very smooth, right? There are some fluctuation or ripple. So we expected that our basically ideal filter should have been like this. Okay. So in the pass band, we expected the gain is 1, which is constant 1, and in the stop band, the gain of the filter is 0. This is what we expected, right? And we have a very transition is immediate, and we thought that it would be our cutoff frequency. But in general, for a practical response, this is not as simple as an ideal one. Okay, so in a practical response, we will find that there are fluctuations. There are fluctuations in the pass band. So this is my pass band, right? And this is my stop band. And then in between, because the transition is not immediate or instantly, that means the slope is not infinity, it has some finite slope, so it takes some transition to go from high gain 1 to gain 0, right? And in the stop band event, it is not exactly 0, but we have some fluctuation above 0. Okay, very close to 0. So we say that this fluctuation, amount of the fluctuation in the stop band is delta 2. Okay, so delta 2 is known as stop band ripple. And we also see that around 1, the gain 1, we have some fluctuation as well. The highest is 1 plus delta 1, and then 1 minus delta 1, and in between we have 1. So we can see that the fluctuation here is delta 1. This delta 1 is known as pass band ripple or fluctuation. We also can see that what is the highest value of h of omega? What is the maximum value of the magnitude of h of omega? This value, right? And this is equal to 1 plus delta 1. We also see that there is a transition band. Okay, so how the transition band is defined? The transition band is defined when it starts the transition, from when your frequency response starts decreasing from pass band to stop, right? So this is the start point and this is the end point. Okay, So the start point is actually the after you finish the pass band. So this is omega p. And the starting of the stop band at that frequency is known as omega s. Okay. So omega p is known as pass band frequency. I mean pass band angular frequency, or in general pass band frequency. Okay. And omega s is known as stop band frequency. So what is the definition of transition band? Transition band definition is actually a delta of omega, which is the difference between the stop band and pass band. Okay. So this is the definition of transition band. And your cutoff frequency of that low pass filter, somehow it is located in between omega p and omega s. That means somewhere in the transition band. Okay. So omega p, the pass band frequency, means once the pass band ends, and omega s, the stop band frequency, means since the stop band starts. Okay, so that is the definition. And omega c, your cutoff frequency, where your so what is the cutoff frequency? The cutoff frequency will be the value of the gain at which it is 70.7% of your maximum gain. So maximum gain is ideally 1, so it is supposed to be 0.707. But when you think about the ripple, it will be 0.707 of the maximum gain, which is 1 plus delta 1, right? So this is how we can define the cutoff frequency. So we always talk about the definition in terms of the ideal response. So that means 0.707 times 1, not 1 plus delta 1. Okay. We ignore the delta 1 for defining omega c or cutoff frequency. Okay. So this is the transition band. Okay. So this is basically the ideal response. So now in this case, we have used the absolute specifications. Okay. Now if you take the relative specification, so then there are some equations for relative specification. So for delta 1 and delta 2, they are used for absolute specification. But for relative specification, what is the relation? For delta 1, the corresponding relative specifications will be Rp. So R means ripple, P for pass band. And for delta 2, the corresponding relative specifications, according to these equations, it is considered as AS. So A for attenuation, it is attenuation. S for stop band. Okay. So we found that we have delta 1 and delta 2 in the absolute specification domain, but we can always go back and forth from absolute specification to relative specification through these two equations. So these equations will be given to you in the final exam. So just remember that these are the equations used to find out the corresponding relative specifications from absolute specification, or the other way around. Okay, so you can also go back to the other domain. And in both case, what is the reference value? What is this? 1 plus delta 1. What is this? Remember, 1 plus delta 1 is the maximum one, right? So in both cases, we actually find out the maximum value. Relative to the maximum one, right? So 1 plus delta 1 is nothing but the maximum value of your magnitude response was 1 plus delta 1. So this is relative. And also this is not only relative in linear scale, but also relative in which scale? Log scale. So it is actually in decibel scale. So whatever value you are getting is in terms of decibel. Okay. So when you plot the same graph, this same graph, which is now plotted in absolute specification domain, when you plot in the relative specification in the log domain, this is how it looks like. Why? The idea is that when you are going to take, for example, log 10, 20, log 10 of 1, because the maximum gain typically for an ideal response is 1, right? So what is that value? Log 1 is 0 dB, right? When you take the value of, that is Rp. So Rp is basically the 1 minus delta 1 divided by 1 plus delta 1, right? This one. Okay. So in this case, it will be my Rp. So it will be negative Because why? Because 1 minus delta 1 divided by 1 plus delta 1. So is it more than 1 or less than 1? This one? It should be less than 1, right? 1 minus delta 1 divided by 1 plus delta 1. The ratio is less than 1. So anything you take of your log value less than 1, that means point something. So it will be negative, right? Do you agree? It will be negative.
Yeah. Yes.
Something, so log 10 of 0.5, this is negative. So you see that it is actually negative. So highest is 0 and then negative. Similarly, AS will be negative as well. Because what is AS? AS equation is like this, delta 2 by 1 plus delta 1. Okay. So again, it is less than 1. So therefore, it is going to be negative anyway. So in a decibel scale or in a relative specification, this is actually your y-axis is actually negative because the highest value is 0 and everything is negative, the other values. All right. So see an example here. We have a passband ripple and stop band attenuation of a digital filter is given by 0.25 dB and 50 dB. So what is given? Is it given in terms of absolute or relative specification?
Relative.
Yeah, because it is in terms of decibel, right? You can easily understand that. And then you have to determine the passband ripple tolerance, or that ripple is also sometimes called as tolerance. Okay, so passband tolerance or passband ripple and stop band tolerance or stop band ripple delta 2. So RP, basically what is given, this is RP, this is AS are given, right? You have to find out delta 1 and delta 2. So use the equation, it is very simple. So now you can see that your RP was 0.25 and AS was 50 dB, but what is the delta 1 and delta 2 values are getting? Very small value, right? Can you see that? Delta 1 and delta 2, very small value.
Yes, sir.
One of the reasons why we take the decibel. Sometimes decibel in log scale, you can make a very high value into very low value, and very low value into and something that is acceptable. For example, when you take, for example, if you have a very high value, let's say 10 to the power 5. So this one we can write down as 100 dB, right? The 10 to the power 5 is a very huge value, right? We can write down this as 100 dB. Now, if you have a very low value, like 10 to the power minus 5, what does that mean? 10 to the power minus 5, very low, very small value, right? We can write down this is as minus 100 dB. Do you agree? So you see that the numbers, when we are dealing with very large numbers or very small numbers, in this case, the example is a very long, very small numbers, right? So when we deal with these very small numbers or very large numbers, in both cases, if we take in the log scale, in decibel scale, it's very easy because now the value is 100, right? Something that is comfortable we are dealing with the number, right? Not 10 to the power 5, 10 to the power minus 5, very high. Well, okay. So that's why another reason why we chose to take the log scale. And relative specification also gives you the idea that how good it is with respect to the maximum value. So this is another part. So since we are normalizing the value with respect to the maximum, as well as you're taking talking about in the decibel or log scale, that means the numbers now suggesting very we can see the physical interpretation of that number, okay, very easily. So this is one of the reasons why we move to relative specifications from absolute specification. Another example where passband tolerance delta 1 and delta 2 are given, you have to find out, so these are the values, you have to find out passband ripple and stop band attenuation. That means RP and AS, right? So the other way around. Previous example, RP and AS were given, you have to find out delta 1 and delta 2. Now this is the just other way around. So very specific. So again, you see that when you have a very low value, delta 1 and delta 2, but RP and AS are getting something, not that low value, right? So this is another reason. Okay, so what is your design goal eventually? So you have to meet the technical specification given and to achieve the frequency response, right? So design goal is basically design a low pass filter first, as mentioned before. Whatever your target filter, final filter, you have to start with a low pass filter design. So what does that mean? That means obtain its system function or its difference equation, or its frequency response, that is h of omega, okay, with a pass band 0 to omega p and stop band omega s to pi, with a tolerance delta 1 in the pass band and stop band tolerance delta 2. So this is exactly what we have said here, okay, in this case. So our design goal is basically to achieve these characteristics, this particular graph, okay, or find out our h omega or h of z or difference equation, such that our pass band, this is our pass band, right? So what is the pass band region? It is from 0 to omega p. See, starting from 0, ending at omega p, right? What is the stop band region? Omega s to
Pi, sir.
pi.
Pi.
Okay, so that is our stop band. What is the ripple? Pass band ripple, delta 1. What is the stop band ripple? Delta 2. Okay. So this is basically our design goal. So achieve a frequency response or a system function or a difference equation of a filter, of a low pass filter, having a pass band of 0 to omega p, having a stop band of omega s to pi, and having delta 1 and delta 2 as pass band and stop band ripple respectively. Now these values are supposed to be given. So what is basically technical specification we found? So in this, all this part, what are the technical specifications? We have technical specification in two ways. One in the pass band region, another in the stop band region. So what are the specifications? We have delta 1, we have delta 2 here. Here we have omega p and omega s. So these values are supposed to be given to us, right? So these are basically the technical specification. A specific value for these will be given. Based on this, we have to design the filter. Okay. Based on this, we have to, for example, find out the coefficient values based on delta 1, delta 2, omega p and omega s. Okay. So now, obviously, no one is going to give you this technical specifications, directly, because if you are required to design something, you have to find out the required technical specification by yourself. Okay. And then based on that technical specification, you have to design that filter. Okay. It's not that easy that it is ready-made available. That if the technical specification is ready-madely available, then anyone can use that. Okay, anyone can use a software tool to feed those technical specification values and design a filter. But that is not as simple as possible. So basically, it's your job to find out the required technical specification, and then based on that, you design the filter. And then finally, once you design the filter, you have to verify. You have to do the validation of your performance evaluation of your filter, so that to see that whether your designed filter actually met the criteria of the required specifications. Okay, so there are steps. So we did talk about some of the FIR filter comparison with respect to IIR filter, right? So for example, the phase response is linear, there is no stability issue and all the stuffs, and efficient to implement. I mean efficient because IIR filter will have two different delay, right? For FIR filter will have only one type of delay, so that's why. We'll skip this three, some of them, and then we'll talk about some of the example. So let's say the impulse response HN is given. Can you tell me what kind of filter it is? FIR, IIR, impulse response is given.
So FIR.
FIR.
It has a finite response in impulse response duration, finite duration of the impulse response, so FIR, right? So if this is HN, then what will be my BM coefficients? What will be my B0, B1, B2? So basically this is B0.
All of them are 1.
B1, B2, right? All of them are 1. Okay. So if I know BM, then should I be able to find out H of omega? Yes, because I can.
Yes.
Yeah. So I can use the DTFT equation to find out H of omega, as simple as that. Okay. So if you are asked that determine and draw the frequency response, so this is the determination of the frequency response. Okay. Now you know that frequency response refers to two parts. One is the magnitude and the phase. So this is something that we talked about before. and then accordingly you can draw that response, right? Anyway, so now for the design techniques, there are different design techniques. Okay, one is known as window design, another is frequency sampling design, and the third one is optimal equitable design technique. For this particular course, we are only going to talk about window design technique. Okay, this window design technique is basically only for FIR filter. IIR filter, window design technique will not be applicable. Okay, so for that particular course, we will only talk about window design. Now, why window comes into our picture? The reason is very simple. We're talking about FIR filter, remember. That means finite impulse response, or in other words, finite duration impulse response. Okay, so the impulse response will have finite duration. To make it a finite duration, you have to cut down from infinite duration, right? So let's say that you have an infinite duration impulse response. Okay, something an infinite duration impulse response like this. Okay, now you have to make it finite. How we can do that? Let's say that I have a window function, okay, having value 1, rectangular window function, and then 0. Okay, so if I multiply our hn with this window function, say wn, so what will happen? If I multiply hn with wn, what will happen in time domain? So I will easily understand that I will end up with only this part, right? Because these are the values under the rectangle that is multiplied with 1, right? Yes, the other will be multiplied with 0. So what will happen? They will become 0.
They will become 0.
Okay. So what I'm trying to say is that from infinite impulse response to finite impulse response, how can we achieve that finite impulse response from an infinite duration? It is possible by applying some kind of window, right? So I applied a rectangular window and then multiplied that rectangular window with that infinite duration impulse response, and then it becomes finite duration. So previously it was IIR, but multiplying with wn or window, it becomes now another hn, but this time it is an FIR hn. Okay, so that's what we are saying, that window design techniques to make an infinite duration into finite duration. Now, based on the type of the window, so in this case, what is the shape of the window? It is a rectangular shape, right? But it can have different shape. Okay, maybe let's say it can have something like this, a Gaussian shape, something like this. It's possible. So based on different types of window, we'll have different performance of our filter, of our FIR filter. Now, for example, if I think about rectangular window, what is the problem and what is the disadvantage? You see that rectangular window has a sharp edge like this, right? This is a 90-degree edge, right? Instant edge. So this instant edge, when you are multiplying and you are actually multiplying with your infinite duration impulse response to make it a finite duration impulse response, it actually creates a high frequency content, because anything that is immediately coming down or any edge that is very sharp or instant, it means that it actually has high frequency, because it changes from value high to low or low to high. It occurs immediately, instantly, right? So what is the delta t time here? It tends to 0. So when you have a time tends to 0, what will happen to your frequency content? It will be infinite, because what is the difference between, what is the relation between f and t? So for example, f equal to 1 over t, right? So if tends to 0, then it tends to infinity. Okay, so that's the point. So when you are using an impulse response like this, a rectangular window with a sharp edge like this, it creates a high frequency content, high frequency ripple. Okay, so these are the high frequency ripple that usually found in the FIR filter. You see? See the ripple that we talked about, the band pass, band stop ripple. Okay, so these are the ripple due to those, sudden cut down of your signal. So this is one thing. Another thing is that when you are multiplying with 1, right? Rectangular window means within the window period you are multiplying with the same value, right? 1. So when you are multiplying with 1 of anything, do you think that the value is actually having any change in the value if you are multiplying with 1? So previously it was like this.
It will be the same.
It will be the same if you are multiplying with 1. So as long as it is within window, you are not changing the values of your original impulse response, right? So that means there is no change in the signal. Okay, so this is one advantage. So for rectangular window, one advantage is that it does not change the signal because it is multiplying with 1 every time within the window, and outside the window obviously it is multiplying with 0, so it makes sense. Okay, but at disadvantage is that it has high frequency content. Okay, so this eventually affects two particular parameter in the filter performance. Okay, so now we'll see one table that will be, so this is an example. Before that we talked about this example. So this example says that what is the impact of your signal in frequency domain when you are multiplying. Okay, so what we have seen over here, this is the time domain. Remember, this is what the time domain. Okay, so window, rectangular window means we're talking about the window in time domain. This is how the shape looks like for a rectangular window. But when we're talking about in frequency domain, our signal, this is our signal. Okay, and this is a rectangular window looks like a sinc function in frequency domain, if you remember your Fourier series. Okay, so you're supposed to know that from Fourier series and Fourier transform and math courses, that if you have a rectangular window in time domain, it looks like a sinc function in frequency domain, and the other way around also. Okay, so this is your original signal. This is basically, this is the frequency domain representation of your h of n IIR. Okay, so if you take an infinite duration impulse response h of n and then you make it convert it into frequency domain, remember this is the frequency domain, then this is how it looks like, 0 to omega c. So you see that this is an infinite duration having an ideal low pass filter, right? This is exactly like an ideal low pass filter in infinite duration impulse response. Then when you are multiplying in time domain, so multiplying in time domain means what? In frequency domain, this is convolution. So if you go back to the convolution properties again, multiplication in time domain is equivalent to convolution in frequency domain. But in our cases, what we have actually said, we said that convolution in time domain is equivalent to multiplication in frequency domain. But the other way around is also true. So this is the other way around that before we never encountered before. Okay, so this is the new thing for us. So, but it is again according to the convolution properties. Okay, so this is what is this? This is basically the window function, but in frequency domain. Okay, so the window function, rectangular window function in frequency domain looks like a sinc function, and this is our infinite duration impulse response, which looks like a ideal filter, ideal low pass filter, right? Again, in the negative side, you have to discard the negative side part. Okay, forget about the negative part of the signal in frequency domain, because negative frequency do not make sense. Again, forget about the negative part. So now that operation, that windowing operation, what you do, if you do the convolution between this one and this one in frequency domain, doing the convolution. Okay, because we were not talking about the periodic convolution, means the circular convolution. Remember DFT for DFT we need a circular convolution. So that is the periodic or circular convolution. If you do this one, we'll eventually get this kind of response. So now, does this response looks familiar to you? So remember that we had a pass band ripple, we had a stop band ripple. Remember, we have a transition bandwidth. Can you see that?
Yes, sir.
Actually, FIR filter response, right? This is an FIR filter response, or in other words, this is basically H of n of FIR. So the corresponding H of n of FIR, if you take that in frequency domain, this is how it looks like. So that's what I'm saying, that IIR filter, you see that who's having higher accuracy, IIR filter or FIR filter? Because IIR filter is actually similar to ideal response, right? It has sharp edge from high gain to low gain, right? It changes immediately. But for FIR filter, we have to sacrifice that sharp edge, right? And now it has a transition, right? Transition bandwidth. Can you see that? Okay, so this is a perfect example when you're talking about FIR filter from IIR filter. Now, why do you still choose FIR filter in some in some applications where IIR filter, we know that it has already close to ideal response, frequency response. Why? Because there are some advantages of FIR filter, right? It has linear phase, there is no stability issue of FIR filter, and it is efficient to implement, right, compared to IIR filter. Do you remember that?
Yes, sir.
Okay. So now we already talked about the rectangular window shape, but there are different types of window. For example, Bartlett, Hamming window, okay, Hamming window, Blackman window. So they have different shape, waveform shape. So let me just show you the shape of the filter. One thing I want to show you is that it's not relevant, but you can see that I have used this keyword to search for FIR filter window types, and that is using Microsoft Bing. Can you see that? And what is the result that is coming out? So this is an example. I hope that you can see the different window type here. Can you see different window type? Rectangular, hand, Hamming, and Blackman window. Yes?
Yes, sir. Yes.
So you can see that rectangular is actually very different from the other, right? Hand, Hamming, and Blackman, they almost look very similar, but they have differences. Okay, they have differences. Now, with the same keyword, if I search for Google, then I can come up with another data, just like this. So let me also show you that, because the search results are different. Okay, so this is it actually shows that on the left hand side the different types of window function in time domain, and on the right hand side the window functions how they look like in frequency domain. Okay. Now in frequency domain, when we're talking about frequency domain, which one has a higher ripple? Can you see that? Which one has higher ripple in the, on the right hand side?
Rectangle.
Rectangle.
Right? So it, and if you think about the frequency point of wise, okay, so which one has higher frequency content? For the other, you see that when the highest amplitude is when it is low frequency around 0, right? And for the highest, if it goes to the higher frequency like region, your ripple actually goes down, right? For the other filter, for rectangular, when it is in the higher frequency region, you have still some high frequency content, right? Can you see that?
Yes.
Okay, so that's the point that I talked about. It has more high frequency content, the rectangular window, than the other one, because the other window function, you can see there is smooth in time domain on the left hand side. Can you see that? Are they coming from high to low instantly, or through some smooth ramp function kind of function, right? So very smooth. So that means that it doesn't have too much high frequency component, rather it has low frequency component. Okay, so the reason of why showing this comparison in time domain and frequency domain also between different rectangular function is that on the time domain, when you see that Hamming and Blackman window, they look almost same, but in frequency domain there is difference, right? There is significant difference. Do you agree?
Yes, sir.
Okay, so this is one thing. So now let us talk about how these different window function they actually going to impact our performance of the filter. Okay, and if you understand that, then our FI filter design will be complete. So now let us talk about this one, this particular, yeah. So this is the table, right? So what it takes, we have different window function on the on different rows, right? And we have a transition bandwidth. So this is an approximate transition bandwidth, this is an exact value. So just forget about the approximate, think about the exact value. Both of them talking about the transition bandwidth, right? And then we have minimum stop band attenuation. Minimum stop band attenuation, that means it is AS. Okay. Now remember, what is the formula for AS? What was the formula for AS? It was like this: delta 2 by 1 plus delta 1, and then taking the log of this one, right? 20 log of this part minus, that was a minus. Okay. So that was the formula for, let me write it down again. So the formula for AS was like this: minus 20 log base 10 delta 2 by 1 plus delta 1. Okay. Now remember that, what do you expect? I mean, if you think about your frequency response characteristics, do you want your delta 2 to be higher or lower? Do you want your delta
Lower.
So that is the ripple. You want the ripple to be as minimum as possible, right? You want delta 2 to be lower. Now from this formula, if your delta 2 is lower, then what will the value of your AS? It will actually become higher. Okay, you can try that. Okay, you can try that. So for example, let's take delta 1 to be some value 0.0015, let's say, and delta 2, let's say it is 0.005. Okay, can you calculate the value of AS for this two part, for these two pair? Can you calculate AS? What is the AS? So delta 2 by 1 plus delta 1 minus 20 log base 10. How much is this? 46 dB. Now change that delta 1 from let us make it even further lower. Okay, that means say 0.8, and sorry, not delta 1. Delta 1 should remain same, but delta 2. So let us change this delta 2 to even lower value. Can you again calculate the value of AS now? So what we have done, delta 2, if it decreases, what happens to AS?
Increases.
Increases. That means which AS will be better? Higher AS or lower AS?
Higher AS.
Higher AS is something that is desired because lower delta 2 is desired, right? Okay. So this is one part. We understand that we look for higher AS for a better performance, right? As far as the stop band attenuation is concerned. So we understand this one. So we want higher AS. Fine. Okay, how about the delta omega, transition bandwidth? So what is transition bandwidth again? From pass band to stop band, whatever the transition is, right? Okay. So do you want this delta omega to be lower or higher? Because if you think about from your ideal response of the low pass filter, then it should be, there should be no delta omega at all, right? Delta omega tends to 0 for ideal response, right? So what do you want your delta omega for a better
Lower.
It will be lower, right? So you want delta omega to be lower. On the other hand, you want AS to be higher. So these are the things that we have. Now you compare this window: rectangular, Bartlett, Hamming, and Blackman. Okay. So which one having? So what is this M? M is the order of the filter. M means order of the filter. So having the same M. Okay. So let's say that we have taken 5 different types of FIR filter using these 5 different windows. Okay. And all the filters they having the same order number. Order of the filter M is M. Same. Okay. Now which one having lowest delta omega? Having the lowest among all this part. So you look at this column and find out the lowest value of delta omega. Which one having the lowest? Which one has rectangular? So can I say that rectangular window is best among all these 5 window functions as far as the transition bandwidth is concerned? Can you say that?
Yes, sir.
Yes.
Okay. For AS, should we look for higher or lower?
Higher.
Higher.
So which one is highest
Blackman.
among these 4, 5? Is Blackman. Okay. So if I take rectangular window function, then I win in terms of delta omega, but I will lose in terms of AS. Do you agree? Because this has the lowest AS, this is highest AS, right? And this is lowest delta omega, this is highest delta omega. But for delta omega, we look for lowest. But for AS, we look for highest, right? Do you agree?
Yes, sir.
routine here. Yeah, so it's not a win-win situation, right? If I take rectangular, I'll win in terms of delta omega, but I will lose in terms of AS. And for Blackman, it's the other way around, right? So there is no win-win situation. Okay, so that is the trade-off. So I have to make a trade-off between the transition bandwidth and stop band attenuation. So this is something that this is kind of decision that I have to make based on my requirement and application. Do you understand? So it's not I mean, win-win situation anywhere. So it always you have to, if you want to achieve something, you have to compromise something. You cannot achieve something without compromising anything. Okay, so you cannot have an highest best stop and attenuation at the same time best transition bandwidth. It cannot have that. You have to compromise the other if you want to win for the first one. Okay, so that is basically and it is depending on your application and requirement. So let's see an example now. Let's say that I have to design a filter with a certain requirement like this. Design a FIR low pass filter with these specifications. Okay. So in this case, the AS is directly given, right? What is my delta omega? What is my delta omega? It is basically omega S and omega P, right?
0.1.
So 0.1 pi. So this delta omega 0.1 pi, is it a absolute specification or relative specification? So when we normalize this delta omega with respect to the maximum value of my delta omega, what is my maximum of omega?
Pi.
It is going to be 0.1. Okay, so this is my absolute specification, right? This is my relative. Anyway, so either way we understand that we can find out the delta omega and AS is given, right? 50 dB. For this 0.1 pi, so let's talk about absolute one for the time being. For this 0.1 pi of delta omega and 50 dB of AS, which rectangular function should we take? And what should be the order of the filter in that case? So if I take this one, for example, I understand that my delta omega is found as 0.1 pi, right? So what is the M in this case?
Pi.
What is the M? 1.8 divided by 0.1. Is it 18? Right? Order of the filter will be 18, right? So if I take order of the filter 18, then with rectangular window function we'll get 0.1 pi. But for Bartlett, how much we should get? 6.1 pi divided by কত হচ্ছে এটা? Same order. 6.1 pi divided by 18 now. কেউ একজন বলো কত হচ্ছে এই ভ্যালুগুলা with m equal to 18? What is the value for Bartlett? Hanning and এটা কত হচ্ছে?
0.34.
এটা কত হচ্ছে?
0.36.
এটা 11 by
61.
61.
Yes, sir.
তাহলে এটার মধ্যে M18 যদি অর্ডার নিই তাহলে আমার 0.15 কোনটা ম্যাচ করতেছে? রেক্ট্যাঙ্গুলার, তাই তো? ডেল্টা ওমেগার পার্সপেক্টিভে। But what was our AS in the example? What is the AS? 50. তো 50 কে আমি এখানে ম্যাচ করতে পারতেছি?
No, sir.
তাহলে কোনটা নেব? আমাকে এখন ডিসিশন নিতে হবে।
কাছাকাছি।
দুইটা একসাথে মিট করতে পারতেছি না, রাইট? Remember we talked about and required specification, target specification, and then we talked about approximation of the specification, right? এখন কি আমরা দুইটা মিট করতে পারবো একসাথে? এটা 0.1 নিলে এটা 21 dB হবে। 50 এর কাছাকাছি কোনটা নিব? এটা নিব না এটা নিব? কোনটা না?
53.
44.
44 কেন নিব? 50
it's more-
আমার হচ্ছে রিকোয়ার্ড হচ্ছে মিনিমাম স্টপ ব্যান্ড অ্যাটেনুয়েশন 50 ডিবি। ওকে, সো স্টপ ব্যান্ড অ্যাটেনুয়েশন বাড়লে ভালো না কমলে ভালো?
বাড়লে ভালো।
53 যদি নিই তাহলে এটা মিট করতে পারতেছি, রাইট? কিন্তু 44
Yes,
যদি
sir.
নিই তাহলে কি এটা মিট করতে পারতেছি? নো, এটার ক্ষেত্রে এটা মিট করতে পারতেছি, কারণ আমার তো মিনিমাম টার্গেট। তো আমি যদি রিকোয়ারমেন্টটা দেখি তাহলে হচ্ছে যে এটার ক্ষেত্রে আমি 50 ডিবিটা মিট করতে পারবো, রাইট? অবভিয়াসলি এর পরের যেটা লাস্টের যেটা সেটা তো আরো ভালো মতো মিট করতে পারবো। তাহলে আমাদের এখন যদি আমি দেখি যে স্টপ ব্যান্ড অ্যাটেনুয়েশন নিয়ে কাজ আমাদের যদি কাছাকাছি যেতে চাই, তাহলে আমাদের এই দুটোর মধ্যে এখন ডিসিশন নিতে হবে, হ্যান না হ্যামিং। এন্ড এই দুটোর মধ্যে ডিফারেন্স যদি ডেল্টা ওমেগার দেখি তাহলে খুব কি বেশি ডিফারেন্স? ডেল্টা ওমেগার ডিফারেন্সটা
না স্যার।
খুব বেশি না। কিন্তু আমি যদি স্টপ ব্যান্ড অ্যাটেনুয়েশনের পয়েন্ট অফ ভিউ থেকে দেখি তাহলে ডিফারেন্সটা তো 7 ডিবি, রাইট? তাহলে আমি যদি একটা ডিফারেন্সটা আসলে পার্সেন্টেজে হিসাব করতে পারি, ঠিক আছে, আমি ধরলাম এটা হচ্ছে আমার রেফারেন্স, যদি এটাকে রেফারেন্স ধরি তাহলে আমি ডিফারেন্সটাকে একটা হচ্ছে পার্সেন্টেজ অফ ডেল্টা ওমেগার যে ডিফারেন্সটা সেটা একটু পার্সেন্টেজ করি। 0.34 মাইনাস 0.36 মানে অ্যাবসলিউট ভ্যালু দিয়ে করি, ডিভাইড বাই 0.34, এটাকে 100 দিয়ে মাল্টিপ্লাই করো, কত হচ্ছে এটা? এটা পার্সেন্টেজ অফ ডিফারেন্সটা কত পার্সেন্টেজ ডিফারেন্স? 5 পয়েন্ট। ওকে, এই ডিফারেন্সটা করো, 44 মাইনাস 53 ডিভাইড বাই 44, এটা কি কত মাল্টিপ্লাই বাই 100%, এটা কত হয়? তাহলে বোঝা গেল কোনটা বেশি, কোনটা সিগনিফিক্যান্ট ডিফারেন্ট বেশি ডিফারেন্সটা। তাহলে আমি যদি এখানে 53 ডিবি নিই তাহলে আমি 20% বেটার হচ্ছে, রাইট? আমার স্টপ ব্যান্ড অ্যাটেনুয়েশন বিকজ হায়ার এএস বেটার, বাট এট দ্য সেম টাইম if I choose this one then I have to lose in terms of delta omega with respect to this one, right? তাহলে এটা কত পার্সেন্ট হচ্ছে? 5.8%. So I can gain 20% and in terms of A's, but I have to lose 5.8%. Or in other words, if you want to gain 5.8% in terms of delta omega, then you have to lose 20%. So which one you are going to choose now? Which one you are going to choose?
হ্যামিং।
Finally, you may want to have Hamming window, right? Similarly, if you think about your, I mean these two with respect to this 0.1, if you say that I have to take 0.1 now, then how much? So if you take rectangular in that case, obviously you are 100% matching with your delta omega requirement, right? Transition bandwidth requirement. But how about the attenuation requirement? What is the percentage of, I mean, you lose? So it is 21 by 53, right? For example, if you choose Hamming, so how much you are losing in terms of delta omega, in terms of AS, sorry. এটা কত পার্সেন্ট হচ্ছে? Exactly. So you can meet 100% requirement as long as delta omega concerned, but as far as AS is concerned, you are losing this part, right? Okay, AS. So now you have to make the decision. All right. Yes, in that case you have to increase the number of order. So then there is another trade-off. When you are increase the number of order, that means you are talking about higher value of your delay elements, right? Higher delay elements. So complexity will also increase. So you can also match. Yes, that's true. You can also match taking this as 0.1 pi, and then you find out what is the value of m in this case?
66.
Exactly. See the order of the filter now, the trade-off. Again, it's a trade-off. So if you take m equal to 66, then you can exactly match both the delta omega as well as your As, right? Do you agree? But in that case, you have to take higher order, very higher order. How much? 66 compared to 18. So more than 3 times, right? Order of the filter. So your complexity also grows. So that's the point. I mean, again, if there is no restriction of your order of the filter, then there is no problem. Then you should choose this one if there is no restriction on the complexity of your filter. But remember that your complexity will grow high. Your daily elements will be higher. Filter size of the filter, the cost of the filter will be higher as well, right? But if there is no constraint given on the order of the filter, then obviously you can choose this one and meet both the criteria. That's right. So the point is that there is no free lunch. Okay, you have to pay. You have to pay somewhere. Maybe not directly for the lunch, but indirectly for something else. That's the point that we are making here. Another part is that when this is also possible to see from this graph is that when you are designing a low pass filter with all the specification, same specification except order of the filter, for example, with order 30, with order 40, and with order 50. So which one is supposed to have a better response? Which one is supposed to have a better response? 30, 40, or 50? Which one? No, 50 will have better
50.
response. Higher the order of the filter, we have seen that higher, better the specifications are made, right? Remember 18 order and 66 order, what was the difference? 66th order, if I take the 66th order, then I can actually meet all the requirements in terms of delta omega and As, right? So here you can see that this is for 30, this is for 40, and this is for 50. And if you think about your ideal low pass filter condition, then it is probably like this. So which one is closer to the response? That one.
50.
What? So higher the value of order, your transition bandwidth is also lower. You can also see from this graph, right? Your transition bandwidth is actually delta omega is inversely proportional to the order of the filter. Can you see in this all these equations divided by m? So these are the delta omega, right? So you can also understand higher the order of the filter, that means your transition bandwidth will be lower, which means it will be more closer to the ideal response. So this is an example that shows the same thing, okay? All right. So time is almost up. So I will make one video or another online class to show you how to design the filter on MATLAB, both FIR and IIR. So next class we'll talk about IIR filter design, the theory part, and then if we get enough time, then we'll talk about the MATLAB implementation of FIR and IIR filter, okay? And I mean, I think I need one more online class to give you the examples on MATLAB for FIR and IIR filter design, and also talk about the project. So I think I need one dedicated class for that MATLAB examples part, okay? So next class we'll be talking about, inshallah, IIR filter design, and then we need one more. So that online class is fine. That online class can be after the final exam, because your final exam does not require you to, do things on MATLAB, right? It's only written. So we can also take that that particular MATLAB based tutorial after the final exam is over, because we still have time for the project. So project deadline is, couple of weeks after the final exam. So that should not be a problem. Rubaiyat Faruqi,
Present, sir.
Anthony, Anthony, Shruti,
Yes, sir. Yes, sir. Anthony present, sir.
Shruti,
Shruti present.
Ananya,
Present, sir.
Abdul Rahman,
Present, sir.
Akib,
Present, sir.
Usman,
Present, sir.
Syed Alam,
Present, sir.
Nadim Mahmud, Nadim, Fardin,
Yes, sir.
Waful Soha,
Yes, sir.
Sumaya,
Present, sir.
Afran Farooq,
Present, sir.
Tarimun,
Present, sir.
Nafisa,
Present, sir.
Tasfiya,
Present, sir.
Imtiaz Abedin,
Present, sir.
Sajid Ahmed,
Present, sir.
Oishi Benazir,
Present, sir.
Mahmud Sajjad,
Present, sir.
Tanzima,
Present, sir.
Hasibul Hassan, Hasibul Hassan,
Present, sir.
Abhishek Dash, Abhishek Dash, Mukti, Mukti, Bobby Shah,
Yes, sir.
Anika Saima,
Present, sir.
Kaji Wafa,
Present, sir.
Khalid Mahmood,
Sir.
Yes, sir.
Sajid Hussain,
Present, sir.
Samara,
Present, sir.
Roman Khan,
Present, sir.
Sir, present, sir.
Kinam,
Sir, Roman.
Yasin Altaf,
Yes, sir.
Afranuzzaman, Tanzir Hassan,
Yes, sir.
Sajid Jafri,
Present, sir.
Sir, Mukti present.
Okay, thank you.